Welcome, Dorothea, again. Nothing else to say. Really, the floor is all yours.
Yeah, thanks so much. And the honor is really all mine. So I'm super happy to be here virtually in Florida. So this is a picture that I took on a Florida trip a couple of years ago, and I'd love to be there again. And so good morning, everybody who has the good fortune of joining from Florida or from the States. And also hello, good afternoon to everyone here in Europe, where it's pretty rainy these days. And good evening to Asia, if there's someone in that time zone too. And I'm super happy to talk about the possibilities of adding visual information to our systems and to allowing our computer systems to not only hear, but also utilize visual information with this. And so with the core idea really being that we humans, we use visual information all the time. So when we listen to someone, we tend to look at them. And we don't just do it for social reasons, but really we look to listen also to understand better what's being said. And this has been established for a long time in the community. So there were very early and very extensive listening tests already in 1954 by Sumbi and Pollack. And they were already able to show that in noise, so in something like white noise, principally like white noise, visual cues were enormously supportive in understanding bisyllabic words. So they used bisyllabic words in a spondaic stress pattern like baseball and such, and had different vocabularies in their tests. And what you can see in their graphs is that, for example, you achieve about a 50% accuracy, so SRT 50 in their test setup at around -9 dB of speech and noise. And then when you add visual cues, again, SRT 50, you move to around -21 dB. So it's just enormously supportive, not only for social reasons, but really for understanding your communication partners. And this has been shown time and again for hearing impaired users, for CI patients, but also, of course, for normal hearing listeners. And what I always find very, very nicely illustrative for this effect that we use visual information in speech perception and even in categorical speech perception is the McGurk-MacDonald effect. And so probably most of you already know it. Nonetheless, I'd like to play it once more. So I hope that my audio is well enabled. Let's see if this works.
Bar, 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 bar.
She's saying bar, 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 right? Yeah, she is. How about now, though?
Bar, 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 bar.
You're hearing far, 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 right? Well, actually, you're not. The audio hasn't changed. It's still bar, 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 bar. Don't believe me? Watch it again and then turn away halfway and you'll hear something completely different.
Bar, 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 bar.
And so I wonder if it worked for you. So Seba or Jan Willem, does it work for you? Does it work over Zoom?
The video
There was a little bit of delay, I think, between audio and visual.
There was a delay. Oh no.
It was good. I think we got the idea, at least.
Okay.
Once that we know it.
So it doesn't work in streaming then. Oh, that is really unfortunate. Okay, so you have to listen to it live. There's if you look for this, then this is really unfortunate.
Oh, maybe we can share the video later in the chat so people can check it out.
I can have a look and share the video in the chat. So
Thanks.
in principle, you should be noticing that your categorical speech perception changes completely when you have inconsistent visual cues that are inconsistent to the video. And this has also been shown in not only in that original, but in many subsequent studies. And of course, the question is why? Why is there this effect? And it seems to be that we're actually integrating visual information in speech perception in multiple levels and in multiple mechanisms. So on the one hand, we apparently, and this is something the McGurk-MacDonald effect really illustrates when the video works, we use it for phonetic disambiguation. So we see the lip movements, and this helps us to determine which phoneme or which phone was currently being produced. And this is one effect that is helpful to improve speech perception in noisy environments. A second effect that's also very important, though, is the support of entrainment. So you know that the speech envelope is represented in the cortex, and this representation is enhanced if you're presented with congruent audiovisual speech. And this integration, this audiovisual integration, really takes place across longer time spans and also in multiple stages of processing. So, for example, you see it in the midbrain and you also see it in cortex. And now our question in our research group is really, how can we utilize those mechanisms to support speech intelligibility? How can we make it possible to support speech intelligibility to an extent that would not be possible with audio processing alone? And for that purpose, we're basically going two different routes. So on the one hand, we're looking at human speech perception as an inspiration for audiovisual speech enhancement. So we try to equip our speech enhancement systems with the ability to utilize this visual information. And on the other hand, we also try to create visual stimuli for supporting human listening. And I will dive into those two in a bit more detail, and then I will conclude my talk today with a few perspectives on privacy, time permitting, of course. And so let's look at audiovisual speech enhancement first. That's actually a topic that's of really significant current interest. And you can see this among others in the multiple challenges that are being organized around audiovisual speech enhancement. So for example, there's the series of audiovisual speech enhancement challenges. On the other hand, the Chime challenge of this year also uses audiovisual data. So the community has really seen the benefit by now that video data brings for speech enhancement, for removing noise and for improving the speaker to distortion ratio, and also even for separating out multiple speakers. So this is of great current interest, and we actually in our team, we already thought that this would be super interesting quite a number of years ago. So in 2016, we started our work on audiovisual speech enhancement using back then HMM, GMM systems. And let me play you what happened there. So let's hear a clean audio sample.
Bin white with L3 again.
That's a sample from the GRID audiovisual corpus. And let's now listen to that sample when it's distorted by additive noise from a Chime challenge. So this is distorted, and as you can see, it's really heavily distorted by household noises, and there's a child in there somewhere. Okay, so this is pretty hard to understand. And then let's have a look at what standard MMSE speech enhancement, audio only, it's Loiseau's algorithm, what that would have done with the signal. And you can see that basically it concentrates on the child rather than on the actual speech. And now when we have visual information available in addition and use this audiovisual state-based enhancement that I just talked about, this is what the spectrogram looks like. So you can see that already the spectrogram is really reconstructed much better. And this is the audio.
Bin white with L3 again.
And so you definitely hear artifacts. It does sound robotic, but it does also really bring out the actual content that was being produced there. And our goal here, our main goal at that point, was speech intelligibility. So what we did is we evaluated the intelligibility of the signals for human listeners. So we carried out listening experiments on a crowdsourcing platform using the original noisy speech at different SNR levels, using the log MMSE enhanced speech, and using 3 different versions of our audiovisual speech enhancement system. And what you can see is word accuracy of the test listener. So we want to achieve the highest possible values. And you can see that with this approach, it's really easily possible to have very substantial improvements in intelligibility for human listeners, although, of course, the quality is obviously not there yet. And so now, currently, what you see is really the same idea, audiovisual speech enhancement, but of course now using deep learning for enhancement. And there's multiple works on this, and we're currently working on this topic with Ferdinand Campo, who's pretty new in our team, and we've worked on it with Yosra Griri as well. And so what we're interested in for audiovisual speech enhancement is to be able to both remove noise from speech, but also to separate out speakers. And so currently we're basing much of our architecture on visual voice by Gao and Graumann, and we're interested in making the system multi-channel and in reducing the latency of the system as far as possible to make it amenable to real-time processing. And so now let's listen to a couple of samples to see what visual voice can do. So this is clean speech first.
I always wanted to be on the stage, and I think when I was around 16 or 17, I went, wow, I've been training my whole life to be like everyone.
We tend to lead the most shattered family lives. You know, you see the repercussions of it at such a young age. We
always
tend to
wanted to
lead
be
the
on
most
stage,
shattered
and I
family
think
lives.
when
You know,
I
you
was around
see the
16 or
repercussions of it at such a young age.
And so those were the mixed audio signals. Now let's see what we can get out from there. So first focusing on her.
I always wanted to be on the stage, and I think when I was around...
And now him.
We tend to lead the most shattered family lives. You know, you see.
And so you see there's still quite a lot of artifacts and still work to be done. But with this being a mixture at 0 dB SNR, I think this is really motivating that with visual information, we'll seriously move the field forward in situations where speech quality is significantly impaired. And so the question now is, how do those systems work currently? What's the state of the art there? And I would like to just give you a very, very brief walkthrough through those architectures. And let's have an overview first. So there's audio feature extraction, video feature extraction, and there's the core of the speech enhancement, of course. Audio feature extraction, there, what happens is exactly what you would expect. So for audio feature extraction, typical choices that you see is the STFT, the short time Fourier transform, and also typical is to work with learned audio embeddings there. Secondly, for the video feature extraction, typical first steps are really that you extract the facial regions of interest. So you want to focus on the face and especially on the mouth region. And once you do have those regions of interest for the speakers you're hoping to enhance, you typically see convolutional networks in different architectures. But there's also, again, work on just using embeddings rather than convolutional architectures. And one feature that is sometimes helpful, though in our work it's been pretty inconsistent, is to use facial or mouth landmarks, where the intuition is that if you can track points on the lips, then this will really help you to get to the movement and thus to the articulator positions. And now, of course, the interesting question is what happens at the core of things. And well, non-surprisingly, there's many, many different architectures you can use for this audiovisual speech enhancement. One central choice, though, that you really are facing is whether you want to make your AV speech enhancement end-to-end. So whether you want to design a system that will really produce clean speech directly. And this is work that you do see currently at this point in time. And I think the jury is out if trying to produce clean speech directly is the way to go, or if, and now there's many, many architectures, if focusing on STFT features as audio features, producing an estimate in the STFT domain and then synthesizing clean speech, if that's going to be the way to go. And of course, obviously, when you work in the STFT domain, that gives you some possibilities that are not obvious when you work with time domain features. So you can get very simple architectures. For example, if you're interested in speed, you can do, for example, binary time frequency masking, where you train your DNN that you have just as a binary classifier, which for each STFT feature just estimates if this is speech or noise. That's one possibility you get in the STFT domain, and it's something that's being done. But binary time frequency masking, of course, has a certain limit when it comes to the quality that you can achieve. And so a more solid approach, in my view, here is to use a real valued time frequency mask, where you have STFT features, you multiply them by a value typically between 0 and 1. And so in this case, training your enhancement DNN becomes a regression problem, where you try to find the optimal ratio mask, which, when you multiply it by the magnitude spectrum of the noisy speech, will give you the magnitude of the clean speech. Or even more interesting, and now this is the technology that underlies visual voice, you could use a complex valued time frequency mask. So you multiply the STFT features with a complex valued mask, your DNN becomes a complex valued regression model still, and your multiplication of the spectrum of the complex valued spectrum that you observe with the mask should become as close as possible to the clean speech spectrum. So those are typical approaches that you see, but more recently in the STFT domain, what's become, I would say, the typical winner of challenges. So I looked at all the winners of the audiovisual speech enhancement challenges of the last years, and what's really becoming the typical winning architecture here is kind of a compromise, which works in the STFT domain. So you do produce by your DNN, though, directly by your DNN, estimated clean short time Fourier transform coefficients, and you do have an explicit synthesis stage to get you clean speech back. And what's also typical is that this processing block will start with an encoder of some manner, will then have subsequent blocks where you do temporal processing, frequency processing, and attention models. Could either be with conformer architectures, or in the so-termed AV grid architecture, it's explicit spatial, temporal, spectral, temporal, and attention-based processing. And then you have a decoder to get you the estimated clean STFT. And so those are the architectures that we're currently really seeing as the winning ones for those challenges. And of course, the condition, now the question is, what do you train on with those models? The condition that you want to achieve is now that the estimated complex valued spectrum really corresponds to the clean spectrum of the target speaker. And what's also possible here, of course, is you can add with this architecture an additional reconstruction loss, where you not only look at the question of whether you estimated the spectrum well, but in addition, you can add a loss which penalizes, for example, bad estimated PESC, so bad estimates of perceptual speech quality or low signal to distortion ratio, low scale invariant SDR. So this is the two versions that we've seen in the most recent AVSEC challenge. And of course, now the interesting question is what will happen in the next AVSEC challenge? And that also brings me to my next point, which I think is very interesting in this field, which is for audiovisual speech enhancement, you really do need large data sets. So early work started, of course, with hugely beneficial small data sets like the GRID corpus or the TCD-TIMID corpus, but in recent work, we're really relying on data with much larger size and with much larger variability. And so those are examples of data that we would also currently be working with.
What really makes a chip is the crunch.
New network of neurons firing in sync with each other inside your brain. It's a new configuration.
So there's the LRS2 and LRS3 data sets, which are based, for example, on TED videos and which have hundreds of hours of speech. And there's new corpora being created all the time. And there's larger data sets also utilizing YouTube, for example, AV speech with 4,700 hours. So it is becoming a game of scales here. There's the VoxCeleb data set with more than 2,000 hours. And of course, what I think is hugely beneficial is really the data that is being provided more and more in challenges like AVSEC or like Chime 9 challenge. And so if you're curious about those challenges, AVSEC challenge is actually still running. If you have in your box an AV speech enhancement algorithm, you still have, I think, until the end of next week to submit something, maybe a little short notice. But even if you don't, have a look at the AVSEC workshop at the next Interspeech in Rotterdam. There's going to be interesting new results to see again. Okay, so this much for audiovisual speech enhancement. Really, I think a very thriving field right now, thanks to the huge developments in both the compute side of things and in the understanding of what we need to do in neural networks to really estimate clean speech well. And now let's move to the second core topic here, to supporting hearing by creating visual stimuli for listeners. And as I said, we know that viewing a speaker's face really supports tracking the envelope of the intended speaker, and that in turn subserves speech comprehension. And so on this topic, we're working currently in a joint project with Universität Erlangen-Nürnberg on neurobiological and algorithmic mechanisms of audiovisual speech processing. And Alexander Wissmann, who might be here, is our PhD student in that topic. And what we're interested in is understanding better how human multimodal speech perception works, how we can predict the intelligibility of AV stimuli, and how we can generate stimuli based on audio only to help hearing impaired listeners understand speech better. And for that purpose, we're looking, first of all, at what characteristics the speech has to have in order to best support intelligibility. And so we've been looking at speech and noise comprehension and generating different level, different quality facial movements to test whether and to what extent they help understand speech. And we've seen there that both natural and simplified facial movements really help in speech intelligibility. And what I think is very, very interesting for us is that we also can see how this effect is linked to cortical tracking of speech in the delta frequency range. So when we look at how much delta frequency band tracking improves by adding a visual stimulus, this is clearly predictive of the intelligibility that we will get. So if a visual stimulus helps us track delta, this is very, very likely to also help us understand. And of course, this brings us to the point that entrainment must be significant here, but still disambiguation of course, is also one effect that we're very convinced plays a significant role in speech intelligibility. And so now we want to successively design better and better visual stimuli to better and better support both the tracking and the phonetic disambiguation. And I'd like to show you a very brief video, which kind of shows the current state of things, but not created by us.
Hello, my name is Dorothea Kolossa. I'm working as a professor at TU Berlin, focusing on human-centered technologies and intelligent systems for fostering health and human connection.
And so if this was kind of synchronous, maybe it was, then maybe you were able to see that almost, but not quite is the right word to describe things here. So the lip movements do look realistic, but we don't really get the expected positions for the phonemes that we're perceiving. And so we're in this project working on different architectures. So, for example, we're interested also in controlling articulators explicitly using something like the Unreal Game Engine to create visual stimuli that are even more supportive of human listening than what you can currently achieve with diffusion and GAN models. And this brings us to the perspectives already. I think I have until 45, right? Until 42. Okay, 3 minutes. Wonderful. So the question is really, can we do multimodal learning and can we still do privacy at the same time? Can we support human listeners by giving them visual information, giving their hearing aids visual information in such a way that we don't need to film our entire environment? And so I don't know if anyone here still remembers how Google Glass really suffered from a snafu. So people were kicked out of bars for wearing glass because the device represented a form of ubiquitous recording and people really didn't like this. And so I don't know if the atmosphere has changed around this, but whether it has or not, we are in our team really interested in trying to achieve privacy and multimodal learning at the same time. So we're actually also starting into a new EU project right now on privacy preserving smart speech technologies. That's an EU doctoral network where we want to focus specifically on the privacy question. And what I would really like to say here is that this is really obviously a trade-off, but it's much, much more favorable than you would typically expect. So there's a lot of technologies that you can use to make privacy-preserving multimodal learning very efficient and also allow for high quality. And one of those, of course, is edge computing, the fact that we have so much more compute power at the edge, either in the hearing device itself or locally on a machine. Then there's also super interesting developments in privacy-preserving video sensing, like Wi-Fi-based sensing, privacy-preserving feature extraction, and there's, in the security side of things, there's differential privacy, federated learning, and the whole thing teamed with gradient exchange, which can really help you make this a win-win situation. I don't want to go into my minimal federated learning example, which really illustrates that federated learning is in a way easy to understand. You can collaboratively learn, each person using their own data and not transmitting their own data. Gradient exchange, where you have a local machine learning model and you just collaborate on a global model by exchanging gradients. So all of these technologies combined will allow you to create models that learns from distributed data, but really brings it together in a privacy-preserving manner. And so to conclude, what I've tried to convince you of is that audiovisual hearing support really is a natural idea, because we do look to listen. We look to understand what's going on in our environment, and we would like to support this. And this idea has been around for a pretty long time. So the idea of using gaze and location information for steering hearing aids, of course, is in the field for a long time. But speech enhancement is something we're seeing recently really thriving. when visual information is added. So we can get significant gains in speech intelligibility when we add visual information. And I think what's going to be a super interesting new type of work is also to use generative models that can create visual cues for hearing impaired listeners, for example, to help them better understand in telephone conversations, to help them better understand when they're listening to, for example, a podcast, so to support listening in situations where no visual cues are per se available. And of course, we need to consider those challenges. There's a multitude of them, and this is what kind of makes our work interesting as well. So firstly, we want to really develop privacy-preserving methods. But what I haven't even really touched upon is the question of reliability, where there's a lot of work to be done to also profit from visual information when it's only intermittent, for example. And latency, of course, is the big issue when you're working on hearing support in real time. And with that, I would like to thank our team with a very old picture from last year. So it's changed again, but our retreat hasn't happened. So soon there will be a new picture. And of course, mainly I want to thank you all for your attention and for being here in Florida. Thank you.
Dorothea, thank you so much. This was such an inspiring talk. A lot of things that you touched on, a lot of points to discuss. So thank you again. It's an honor to have you. I will start just by looking. There's no Q&A questions here. One question in the chat by Jan Willem that I would like to kick off with. So get ready for more to come. I have many, so we'll think how to manage with the time. So the first question that we have from Jan Willem is, let me go up here, is, do you know if there are databases of atypical speech, like deaf speech, or people
that is very interesting.
who had surgery to their vocal tract, where he is saying, actually, I imagine that for this group, lip reading is extra important, actually, right? Have you worked with such
this is extremely, this is such an interesting and important question, and I haven't come across such data, but it would be extremely interesting to have it. Yes.
Another hint. Yeah. There in the chat, you will find they do exist by Will Widmer, at least for dysarthritic, we'll see how that is pronounced, speech, such as the Torgo database. So have it there. So the answer, you have the question and you have the answer. This is how this conference is, it's like, it's all good. And the second one that I see here, well, I will go first to the Q&A. So we see the first question coming in. So I was not able to file this talk on YouTube channel. Could someone please add the link? That's an easy question. We will get to that, no worries. Well, I guess the other is another comment from Jan Willem saying that when synthesizing atypical speech, do you restore a cleaner atypical speech version, less noise, or do you normalize the voice, easier to understand?
So this is really also an interesting point to consider, and I guess the question would be, first of all, when you try to get to best intelligibility, which one is going to be the right way, or is it actually a combination? So you have those multiple different effects here. When you have atypical speech, maybe the rhythm is also changed, and since you do want to retain synchrony, most likely, as much as possible between the acoustic cues that you create and the talking speaker that you see, there will be some constraints that will likely keep you from wanting to normalize out all the changes. But I suppose that there's also a trade-off involved. So the more you normalize, the easier it might get on the other hand. So there's those two contravening effects. And
very good points. Very good points.
Yeah, maybe if I can add something, this may be the question also about identity. Because to give an example, I trained a system for synthesizing my voice in English, and then I spoke with an American accent. That was funny.
Yeah, that
And I can
is
imagine
also,
if you stutter or if you have an atypical speech and you hear yourself, but then different,
with
it's you,
this
but it's also not
normal
you.
speech. Yeah. So you would want to give the user, I mean, the speaker, some control, right? You would
I guess
want
so,
to
yes.
I guess
help.
it's gonna get better and better with new technologies as well. So that's where the current is kind of going, probably.
Yeah.
I would like to shoot another question, just to step backwards. As you mentioned, like vision and hearing are both important, both complementary, and that's also super important in the cases that you have a sensory loss, either visual or audio, right? So that's also when you have to compensate one, two, or the other. So I wonder your thoughts about how we normally or nowadays how the people with this type of sensory loss are clinically diagnosed or tested, because they go to the ENT department, they treat their hearing, they go to the ophthalmologist department,
and they would not
so should we
given
consider
any
a way to evaluate them both together? Should we
audio
add a
visually.
clinic towards that?
This
What are your
this
thoughts
would
about?
add quite a bit of complexity. So that
Do you think
So currently there is no setup really to have them tested in their audiovisual speech perception. So
I see you're going with that. You're stating the importance of it, but at the same time, we don't have any
we don't have established standards of care even yet, because it's so early in the development of these methods.
Okay, good things. I still just want to make sure we are not missing any question. Also, you're raising very interesting points about privacy and everything, and more technologies coming with glasses with cameras, and now before, as you mentioned, the example of the Google Glass, where it was like such a novel thing, an obvious thing you have in your face that that's new technology, get away of the bar or whatever you mentioned before.
And so currently with the Aria glasses, it looks like people are more curious, let's say, than hesitant.
And also they are becoming less so obvious that you're in a camera or a
But
microphone.
nonetheless, I mean, the question is it okay, even if people don't kick you out of the bar, to film there and to
So certainly it's happening right now, right? So I see people here in the US that those Ray-Ban Meta glasses are used somewhere there. And I see them recording, sending things. So this is just going to happen, apparently. So what are your thoughts about how they are controlling this and how things should be controlled?
So my personal opinion really on this is that privacy is not only something that I'd like to do for myself, but it feels also like a bit of a responsibility to protect. So we really want to develop technologies in such a way that they will, as far as possible, prevent bad things from happening unintentionally, or possibly through a combination of, design that wasn't careful and some malevolent actors, which could be, of course, both coming from, like, let's say, non-state actors, but also could come even from people who are actually wishing our democracy harm. So if we are moving into a society where it's becoming more and more typical that all our data are available online or can be achieved through some easy hacks, then I think we're really running the risk of becoming, first of all, easy to model in a way. I mean, it's surprisingly and sometimes frighteningly easy to model what somebody will want, right? We can see it from the ads we get. But of course, this also extends to what we want in the political sphere. And if we become too easy to model and too easy to predict, it's also too easy to change society with minimal interventions. And I think in research, we should really keep this in mind when we design technologies. And so for myself personally, I'm only interested in developing technologies where I feel safe enough that this is not a possibility, this type of misuse of what we're doing. And I know that this is a huge debate. And of course, there's the desire to do good, and there's also the desire to develop the best technology most quickly. And I can understand that, but I really hope that everybody sees this risk that there is, and that people are aware that it is possible to design in privacy-preserving manners.
Yeah, yeah. So I see one last question there. I will quickly, maybe you can answer real quick from Niels Peter. Is there a minimum video quality or pixel size at which you can measure and improve speech understanding? Maybe you can answer real quick.
Yeah. So the grid corpus that had a low res and a high res version. I don't know off the top of my head the low res, but I think it was something in the order of 250 times 360, and that was easily supportive of speech intelligibility. And it's my intuition that since entrainment also plays such a significant role, probably you can do a lot at pretty low qualities already, but the disambiguation part, of course, will rely on you getting the articulatory movements correct.